Hello students, welcome back to this channel, and today we will study about heap data structure and heap sort. So you must have studied all kind of sorting algorithms. Now heap sort is a different kind of sorting. Now before proceeding to heap sort, we will first learn what is a heap data structure. And before proceeding to heap, we should have a little bit of idea about binary tree. Now what is a binary tree? You must all be aware that a binary tree is like this tree which is drawn here is a binary tree. Why is it a binary tree? By represents 2. A tree which has 2 children is known as a binary tree. See, in this figure you can see the root node has 2 children B and C, and then similarly now B is its child node, the parent node of which is A. B also has 2 children which are D and F, and C also has 2 children G and H. So what is a binary tree? A binary tree is a kind of tree in which every node can have at most 2 children and all its levels are complete. So this is a binary tree. Now a binary tree data structure can be represented using 2 methods. Now you should have a little bit of idea about how a binary tree can be represented, because this kind of tree cannot be drawn in a code. Using a code you cannot draw this kind of tree. We will represent it using another data structure which can be an array or a linked list. Now array representation of binary tree. The tree which we saw in this figure can be represented using array like in this manner. See, A was our root, so A is here, and its left, it is always left aligned. When we are using array representation of binary trees, we use one-dimensional arrays to represent it. Now, see, in this example, A was our root, B was the left child, and C was the right child of the root. So we will represent it like this, in this manner: A, then its left child, then its right child. Then where does this D come from? D is the next level of the tree. Okay, so then D, then F, then G, then H. Now what will we do? Where does this I and J come from? I and J were the children of D, and similarly K is the right child of G. Now how we will write it? We will leave 2 spaces blank for child nodes of F here, okay, and then we will represent K in the array like this, okay. Now there are 2 cases to do the indexing. The first one is when you do the indexing using I equals to 1, okay. Now usually whenever we are doing indexing in arrays, we start numbering from 0 or doing indexing from 0, okay. But and in that case, when you have done your indexing of the array, what kind of indexing I am talking about? I am talking about this indexing. See, if you are starting to locate the your array values from using 0, 1, 2, 3 and so on, then this case applies. What happens? The left, if the node is at ith index, see, our root is at 0, so I equals to 0, then left child would be at 2 into I plus 1 location. So where will the left child be? 2 into 0 plus 1 is 2, index 2. See, this was our root, okay, and इसका लेफ्ट चाइल्ड किधर था आपका 1 पे, एंड राइट चाइल्ड था आपका 2 पे, 0 1 2 3 4 5, I'm sorry, 4 5 6 7 8 9. Okay. Abhi, according using this formula, we can figure out that the left child will be at 2 into I plus 1 location. So our root is at, if our node is at 0 location, then using this formula, the left child should be at location 1, right? And formula हमारा क्या था? फॉर्मूला था हमारा 2 इंटू आई प्लस 1, ठीक है. आई हमारा क्या है? आई इंडेक्स डिनोट कर रहा है किसकी? रूट नोड की और पेरेंट नोड की. सो यूजिंग दिस फॉर्मूला द लेफ्ट चाइल्ड इज 2 इंटू 0 प्लस 1 विच इज 1. ओके, इससे हमें क्या पता चला? लेफ्ट चाइल्ड हमारा क्या आएगा? फर्स्ट लोकेशन पे, और एरे में कहां पर था? फर्स्ट लोकेशन पे. इसी तरह अगर हमें राइट चाइल्ड कैलकुलेट करना है तो राइट चाइल्ड वुड बी एट 2 इंटू आई प्लस 2 लोकेशन. सी, राइट चाइल्ड के लिए फॉर्मूला है आपका 2 इंटू आई प्लस 2 लोकेशन. 2 इंटू आई विच आई इज करंटली 0, सो 2 इंटू 0 प्लस 2 gives 2. So we can find out the right child is at 2 location, and array maybe you can check the right child is at location 2. So these are the formulas you're going to use if you want to know where your left child or right child of the parent node is when you're doing representation using an array. Now this was the case when you are doing numbering or indexing from 0 up to n. What about the other case? If you want to do indexing not like this but from 1 up to n, what will we do? See, now what we are going to do? We are going to do the indexing from 1, 2, 3, 4, 5, 6, 7, 8, 9, dot 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 up to n. Okay. So now how you will calculate the left child or right child? Let's see this case. Our I is at 1. Now let's go through it. When indexing of the array starts from 1, if a node is at ith index, your index is 1. The left child would be at 2 into I location. So left child will be at 2 into I is 1, 2 location, and the right child would be at 2 into I plus 1 location. So 2 into 1 plus 1 is 3, location 3. Your left child is at here, right child is at here. Next अगर हमारा नोड है D, D की इंडेक्स है 4. So how will you calculate its left child or and right child? Now our see, अभी मेरा रूट नोड है या पेरेंट नोड है. I'm sorry, it's there is only one root in a binary tree. The others are its parent nodes. They cannot be called root. Okay, so my parent node is D, which is at index 4. How will you calculate its left child and its right child? See, for left child you're going to use the formula 2 into I. And what is the value of I here? It's 4. Let me get the eraser out. 2 into 4 gives 8. So using this formula you can find out that the left child of D, which is at index 4, lies at 8 location. We should check using the tree. This is our tree. Okay. अभी आप इसका चेक करिए, 4th पोजीशन पे आपका क्या था? D. ठीक है, अभी इसकी हम इंडेक्सिंग चेंज करते हैं। ये हमने 0 से कर रखी है नंबरिंग, अभी हम इसको 1 से करते हैं, बिकॉज अभी हमने क्या चेंज कर लिया है, फॉर्मूला चेंज किया है, टेक्निक चेंज की है। सो लेट मी जस्ट इरेज दिस। One, 2, 3, 4, 5, 6, 7, 8, 9, 10. ओके, तो अभी मैंने इसकी इंडेक्सिंग कर दी। वेयर इज माई रूट? माई रूट इज एट 1। लेफ्ट चाइल्ड के लिए फॉर्मूला क्या था? 2 इंटू आई। 2 इंटू 1 गिव्स 2। लेफ्ट चाइल्ड निकल गया इसका लोकेशन 2 पे। राइट चाइल्ड के लिए फॉर्मूला था 2 इंटू आई प्लस 1। 2 इंटू 1 प्लस 1 इज 3। राइट चाइल्ड कैलकुलेट हो गया। नाउ वी वांट टू कैलकुलेट व्हाट? लेफ्ट चाइल्ड ऑफ दिस नोड। व्हाट इज इट्स इंडेक्स? इट्स इंडेक्स इज 2। then its left child will lie at position 4, which is clear from this diagram that its left child is lying at index 4 only. Now how will you calculate its right child? Right child can be calculated by using formula 2 into I plus 1. So 2 into I plus 1 gives 2 into, what is I here? I is 2, right? So 2 into 2 plus 1 is 4. Okay. So in this way you can calculate whichever is the left child and whichever is the right child of the parent node, if you are doing the representation using an array. I hope it's clear, and if there are any queries or any questions, you can write down in the comment box. I'll see them and I'll manage to solve them as earliest as possible. Now let's come back to heap data structures. What is a heap data structure? Heap is a special case of balanced binary tree data structure where the root node key is compared with its children and arranged accordingly. If alpha has a child node beta, then key of alpha is greater than or equal to beta. As a value of parent is greater than that of child, this property generates max heap. Based on this criteria, a heap can be of two types, a max heap or a min heap. Now, let me show you something. Okay. Suppose this is our tree. What kind of tree? It is a binary tree. We just studied what a binary tree is. Okay. Now, do you notice this is our parent node. Its child nodes are 42, 35, 33, 10, 26, 31, 14, 19, 27. Now, there is one common property in each of the parent nodes. What is it? See, this is the parent of these two nodes. These are its left and right child. But the value of the parent node is greater than both its children. Similarly, in this node you can see that this is my parent node and the value of this node is greater than this child, its only child. And here also you can see that if this is my parent node, the value of this node is greater than its all of the children. Same property follows here. 35 is greater than 19 and 27. Now coming to the root node has the maximum possible value in this binary tree. Now the point is, if you see any kind of tree like this, then we can say that it is in max heap form. What do we call it? We call it max heap. When the value of the root node is greater than or equal to either of its children. Now, where do we use max heap? We build a max heap for doing heap sort. Okay. Now similarly, there is another property called min heap. Min heap, as it is clear, it is quite clear from its definition or its its vocab. Min heap, what does min heap suggest? That the parent node or the root node has the least value. Now see this tree. Here, this is my parent node 10. And this is also the smallest node in this complete binary tree. Okay. So that's what my point is. In a min heap, the value of the parent node is least value. Okay. You can see that this is my parent node and its value is smaller than both of its children. Similarly, this is my parent node and its value is smaller than both of its left and right children. And the parent node has the smallest value. I hope that's clear that this is called a min heap. Now coming back to max heap construction algorithm. Let's go through the steps first of all, and then I'll explain you how to build a max heap, and then I'll explain you how to build a min heap. Step 1, create a new node at the end of the heap. Whenever we are going for max heap construction, first of all we will create a new node. Step 2 is assign a new value to the node. Step 3 is compare the value of its child node with its parent. Step 4 is if value of parent is less than child, then swap them. Step 5 is repeat step 3 and 4 until heap property holds. Now heap property, what is a heap property? Whenever you are going to construct a max heap, the heap property says that the parent node should be greater than its child nodes. And whenever you are going to construct a min heap, then the property says that the parent node cannot be greater than the child node. See, that's the difference. Then that is also the property of max heap or min heap. Now in min heap construction algorithm, we expect the value of the parent node to be less than that of the child node. That I already told you. In min heap construction, the value of the parent node should be less than the child node. See, this is our input 35, 33, 42, 10, 14, 19, 27, 44, 26, 31. Now you want to build a max heap. How will we do that? First of all, insert the first node here, which is 35. Okay. Then my next node is 33. It will always be inserted here because a heap is a binary tree and a binary tree is always left aligned. So all insertion is always done from left to right. Keep that thing in mind. There is a huge difference between binary tree and binary search tree. No, BST properties do not follow in a heap tree. Okay. Now next node to be inserted here is 42. Where we will insert 42? Okay, one step is, I forgot to tell you that, suppose this is my insertion done here. What will I do after insertion? I will check the value of the child node, that is it smaller than the parent node or not. Here we are doing max heap. Okay. So after every insertion, what we will do, we will check that the child node cannot be greater than the parent node. Okay. This we will check after every insertion. Now you've inserted here 33. Did you check that is 33 greater than 35 or not, or 35 is greater than 33 or not? We did not, so we will do this. Then we will proceed with next insertion. Now is 33 smaller than 35? Yes, it is smaller than 35. Now let's go to the next insertion. Where will 42 be inserted? 42 will be inserted as its right child. Okay. Now compare the value of the right child node with its parent node. Is 42 smaller than 35? No. Now that violates the property of max heap. What we will do? We will swap them. Okay. Why we will swap them? Because it is greater than or equals to greater than 35. Okay. So what we will do? We will just simply, now 42 will come here and 35 will be inserted here. Now let's do proceed with the next insertion 10. Where will 10 be inserted? 10 will be inserted in as a left child of 33. Now check, is this in max heap form? Is 10 less than 33? Yes, it is in less than 33 and the rest of the tree is already in max heap. Now let's go to the next insertion, which is 14. Where will 14 be inserted? Obviously 14 will be inserted as the right child of 33. See, now compare. After every insertion, what we have to do? We have to compare these values. Now, is it in max heap or not? Is 14 smaller than 33? Yes, it is smaller than 33. So, we will do nothing and proceed with the next insertion. Now, next element to be inserted here is 19. Where will it be inserted? It will be inserted here. Now, again check, is it in max heap? Yes, it is in max heap. It is the greatest value is at the root and rest of its nodes are smaller than the parent node. Now let's proceed with next insertion. Then our next node to be inserted here is 27. Where will 27 be inserted? 27 will be inserted here. Check again, is it in max heap? Yes, it is in max heap. So next node, insert the next node, which is 44. Where will it be inserted? It will be inserted here. Okay, why are we doing insertion from here only? Because a heap data structure is a binary tree, and in a binary tree we always do the insertion from left to right. First all its levels are completed, then we proceed with next insertion. Now we have inserted 44. Check, is it in max heap? Is the child node smaller than the parent node or not? No, it's not in max heap. So what we will do? We will swap these values. So 44 will come here and 10 will be swapped with it. Now we have swapped these values. Now check again, is it in max heap? No. Why is it not in max heap? Because this value is still greater than the parent node. What we will do? We will swap again. We will continue the swapping until the parent node has the maximum value element as the root. The root of the tree should be greatest value, but it is not in max heap right now. So what we will do? We will swap again these values. What will happen? 33 will come here, 44 will be placed here. Now check again, is it in max heap? No, it's not in max heap because 44 is greater than its parent node, or the root node is still not the maximum possible value. What we will do? We will do the swapping again. So simply insert 44 here and 42 will be inserted here. Now check, is it in max heap? Yes, it is in max heap. Now we can continue with the next insertion. Now which element is to be inserted now? 26. Where will it be inserted? 26 will be inserted here. Now check again, is it in max heap? 44 is greater than the 42. Now 26 is the smallest value, is a very small value compared to its parent. So it is in max heap. Next node to be inserted here is 31. Where will 31 be inserted? 31 will be inserted here. Now check again, is it in max heap? Let's check, 31 is greater than its parent node. So what we will do? We will perform swapping. So now 14 will be inserted here. Right, and which was our last node? 31 will be inserted. Sorry, 31 will be inserted here and 14 will be inserted here. Now check again, is it in max heap? Yes, it is in max heap. So this is our final max heap. So we just learned how to build a max heap. Okay. In next lecture, I will teach you how to do heap sorting using this max heap construction. Okay. So similarly, okay, for heap sorting, now you know how to do insertion in max heap. Then you will have to learn how to perform deletion in a max heap. Okay. Then you can perform heap sorting. We will continue with this topic in next lecture, where I will teach you about main heap and heap deletion. Okay. And I will tell you one more topic, which is Huffman algorithm. So I will see you next lecture. Till then, I want you to go through this topic. If you have any problems, you can post it in the comment box and I will try to solve them. Okay. Thank you so much.